Hey folks, in this video we talk about the action potential. So in the previous video we talked about the resting potential, how your neuron is polarized, and we go through a lot of work, put a lot of energy into polarizing that neuron, concentrating that sodium on the outside in particular, and setting up diffusion pressure so that the neuron is ready to pop, ready to send sodium into the cell like opening up a pop can. So how do we change that? How do we change that resting potential? Well, we can influence that polarization. We can move it up and down. We can do that in a couple different ways. Number one is you can do it through stimulation or from chemical activity. So literally there are receptors in your skin that if they are touched, they get stimulated, and that changes the potential. They're set up to change that resting potential just by touch or by heat or by pressure. Or chemical activity can do it. So there's receptors on your tongue and in your nose that through a chemical process can literally change the resting potential, change the chemistry so that it's no longer so negative anymore, or maybe more negative. The other way we can do it that you're probably familiar with is that one neuron can influence another neuron, and this is going to happen at the synapse. We'll have a whole video about the synapse next, but you can change the polarization of your neuron by influencing it from other neurons. One thing to keep in mind is that when these connections happen between neurons or from chemicals, that kind of thing, they can be excitatory changes or inhibitory. And excitatory changes are going to be sometimes referred to as depolarizations, right? Because it's a little confusing, right? So we're starting polarized, we're negative, we're on the negative pole, right? And we're going to depolarize, we're going to get a little more positive. But we're still polarized, we're at like negative 70, right? So if you go up by 2, we're now at negative 68, we're depolarizing a little bit. That's excitatory, it's positive charge going in, depolarizing. Or your neuron can be hyperpolarized through inhibition. So I can start at negative 70 and I can actually go down from there and go down to negative 72, negative 73, negative 74. Those are inhibitory hyperpolarizations. Okay? So one neuron connecting to another neuron can excite it or inhibit it. And then we can have multiple connections, some doing different things. Okay? So we're going to start at rest, and now we're going to try to change that by exciting or inhibiting, depolarizing or hyperpolarizing the neuron. And we're going to see what happens. Walking through specifically how this works at synapses, which is the connection between two neurons. Neurons in presynaptic send neurotransmitters across the synapse, right? So you've got one neuron before the synapse and the other neuron on the other side. We're going to send neurotransmitters across the gap. Those can create what are known as EPSPs, excitatory postsynaptic potentials, or inhibitory postsynaptic potentials. And this is just what we were talking about on the previous slide, but it's happening from neuron to neuron. Okay? An EPSP is going to look like this. We stimulate it, it goes a little more positive or a little less negative, right? An IPSP is going to hyperpolarize. Okay? At some point, and that point is somewhere around negative 55 millivolts, we're going to hit what's known as threshold. Okay? You see that threshold here. Once you hit that threshold, the neuron will fire what's known as an action potential. Okay, so we've got these little EPSPs and IPSPs. Those aren't action potentials. These are just a little bit of excitement and a little bit of inhibition. Okay, if you get up to negative 55, that'll be threshold. And then we run this action potential, and we go all the way up into the positive zone. You see it ranging all the way up into plus 50 something on that graph. So excitatory postsynaptic potentials, inhibitory postsynaptic potentials. If you get enough excitement, we hit threshold, we hit the action potential.
In a previous video, you learned about the resting membrane potential. In the present video, we want to ask, what can affect the resting membrane potential?
If you want to see this worked out in a cartoon.
When a neuron fires, it releases chemicals called neurotransmitters from its presynaptic buttons. Those neurotransmitter molecules travel across the synapse and bind to specialized receptor molecules on the membranes of the postsynaptic neuron. When neurotransmitters bind to postsynaptic receptors, they typically have one of two effects. The first possible effect they might have is to hyperpolarize the receptive membrane, that is, increasing the polarization of the membrane potential. We can see this hyperpolarization as a downward deflection of the oscilloscope. Postsynaptic hyperpolarizations are called inhibitory postsynaptic potentials, or IPSPs, because they decrease the likelihood that the neuron will fire an action potential. The second possible effect that a neurotransmitter might have when it binds to a postsynaptic receptor is to depolarize the receptive membrane, that is, decreasing the polarization of the membrane potential. We can see this depolarization as an upward deflection on the oscilloscope. Postsynaptic depolarizations are called excitatory postsynaptic potentials, or EPSPs, because they increase the likelihood that the neuron will fire an action potential. EPSPs and IPSPs travel passively from their sites of origin on the postsynaptic membrane in much the same way that electrical signals travel through an electrical cable. The speed of transmission of postsynaptic potentials is so rapid that it can be considered instantaneous. It is important to note that both EPSPs and IPSPs are graded responses. That is, they can be any one of many different sizes, all depending on the strength of the stimulus that elicits them. One last thing to note is that the transmission of EPSPs and IPSPs is decremental. The size of EPSPs and IPSPs decrease in amplitude as they travel across the neuron. In summary, EPSPs and IPSPs travel very rapidly, they are graded responses, and they are decremental in nature.
One thing about those action potentials, once you reach threshold, is that they're all or none. So either you're going to get excited enough to hit the action potential at the threshold or not. Okay, you don't just get a little bit of an action potential or a really strong action potential. It either hits threshold and goes or doesn't. Okay. But that doesn't mean that each signal, so you get a signal from this neuron to that neuron and it excites a little bit. That doesn't mean that each signal needs to be strong enough to get to threshold, because we can integrate multiple signals. Okay, so if I'm a neuron and I'm sitting here at rest at negative 70 millivolts, I can get a little bit of excitement here, a little bit of excitement here, and I can integrate them together to add them up. And there's two versions of this integration. One is called spatial summation from different spaces. Okay? So I can get two EPSPs or two IPSPs or a combination from different sources, from here and from here, from different space, right? So I'm sitting here, one comes this way, one comes this way, different dendrites, right? From here and from here, and I add them up. And temporal summation is over time. Temporal means time. So where you have two or more signals, EPSPs or IPSPs, from the same source, right? But just right away. So boom, 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 boom. Okay. The neuron itself processes these, and it's going to sort of add them up. Okay, add up the EPSPs, add up the IPSPs, and see where we end up. Let's walk through this just quickly because sometimes these ideas are difficult. So here's spatial summation wrapped out. You see we've got one neuron here with presynaptic neurons connecting A, B, C, and D. Okay. And what you should see, sorry, we got A, B, C, and D. And what you see here is that you can get two postsynaptic potentials from different sources, and we can integrate them in a few different ways, right? So if I have two IPSPs from A and B, right, then A is going to give a little bit of EPSP, B is going to give a little bit of EPSP, but when they come together, right, we get A and B added up, spatial summation. Different space, summing together. Cool? So now I get more excited. I'm getting closer and closer to threshold because I got a signal from both A and B. This can also work for IPSPs, right? So this one's going to inhibit, this one's going to inhibit as well, C and D, and they're going to get added up, and now we're even less, even more polarized. Okay. If I get an EPSP and an IPSP, they're going to cancel out. +1 - 1 ends up with 0. Cool? So these all get added up. I'm going to get signals from a bunch of different sources. If I'm a neuron, I'm going to get IPSPs, I'm going to get EPSPs, all essentially exciting or inhibiting that neuron, and that's going to get added up. If it eventually reaches threshold, it'll fire an action potential. If not, it'll just kind of play around in this area, getting added up and subtracted, and no action potential will fire. Temporal summation works in a very similar way, right? I can take two signals and add them up, but in this case, they're not coming from different places. They're coming from the same place. So I've got neuron A connecting to this neuron, and neuron A, if it fires twice over a long sequence, right? It fires again. We're going to get a little EPSP, we're going to get a little EPSP, and nothing much is going to happen. But if neuron A fires twice right in a row, then it's going to fire, and then it's going to get added on. It'll get summed on here if they're occurring closely in time. Same thing for the IPSPs, just in the opposite direction. Inhibit. But if it happens closely in time, inhibit more. Cool? So our neurons are constantly taking signals from different places or spaces and across time, and then adding all of that up. Okay? And your neurons are getting inhibitory signals and excitatory signals, essentially preventing them from firing, or if it's inhibitory, or exciting them to potentially fire if we reach threshold. Okay? And so you can see how quickly this gets complicated. Each individual neuron is integrating information from, potentially a dozen sources over time and deciding whether to fire or not based on that information. Your book has a video on this integration process as well, so check that out if you're in my class and you need a little more.
Neurons are covered with many synapses, and whether or not a neuron fires is determined by the net activity of all those synapses. That is, a neuron's firing depends on the balance between excitatory postsynaptic potentials, the EPSPs, and inhibitory postsynaptic potentials, the IPSPs, that are reaching the axon initial segment. Recall that EPSPs and IPSPs are created by the action of neurotransmitters at receptors. EPSPs and IPSPs are conducted rapidly and decrementally from their site of origin to the axon initial segment. If the sum of EPSPs and IPSPs reaching the axon initial segment at any moment is sufficient to depolarize the membrane above the level known as the neuron's threshold of excitation, then an action potential is generated. An action potential is a large, rapid reversal of the membrane potential. For example, an action potential might involve a reversal of the membrane potential from about -70 to about +45 millivolts. If you recall, EPSPs and IPSPs are graded responses. By contrast, action potentials are all or none responses. That is, they either occur to their full extent or they do not occur at all. In summary, a multipolar neuron essentially adds together or integrates all the graded excitatory and inhibitory postsynaptic potentials reaching its axon initial segment, and then decides whether or not to generate an action potential on the basis of their sum. Neurons achieve this integration of incoming signals in two ways, over space and over time. This is usually known as spatial summation and temporal summation, respectively. Let's look at spatial summation first. Spatial summation occurs when the EPSPs and IPSPs from different locations on the neuron make their way to the axon initial segment and summate there. As you can see, the outcome of that summation depends on whether we have EPSPs and IPSPs summating. Let's take a closer look at the spatial summation of two IPSPs in slow motion. Let's take a closer look at the spatial summation of one IPSP and one EPSP in slow motion. Let's take a closer look at the spatial summation of two EPSPs in slow motion. Now let's look at temporal summation. Temporal summation occurs when the EPSPs and IPSPs from a single location on the neuron make their way to the axon initial segment and summate there. As you can see, the outcome of that summation depends on how closely in time the EPSPs or IPSPs from one particular synapse occur. Let's take a closer look at the temporal summation of two IPSPs in slow motion. Let's take a closer look at the temporal summation of two EPSPs in slow motion. In summary, each neuron continuously integrates the many signals from the many synapses covering its membrane over time and space.
Okay, so I'm adding up EPSPs across space and across time, and I'm adding and competing those with inhibitory signals called IPSPs. Eventually, I might get enough EPSPs to reach threshold, around -55. And then we already learned that that's going to create an action potential where we rush up into the positive zone and we get the real action of the neuron. Well, what the heck even is that, right? To talk about that, we have to go back to chemistry, right? We've got three phases of the action potential, and we're going to have chemistry accounting for these three phases. The first phase is the rising phase, and in the rising phase, all that happens is once you hit threshold, -55 or so, that's going to open up voltage-gated ion channels. So those channels for sodium that were closed open, right? So we hit threshold, that opens the gates. Sodium rushes in, right? Remember, we set up the resting potential to make sure that we've got a bunch of sodium concentrated on the outside and a negative charge on the inside. So we've shook up the pop can, and we're ready to have sodium rush in with all that diffusion pressure. So all we have to do for an action potential is open the gate, open the can, right? Open the voltage gated channels. Sodium rushes in, and we're going to move from negative 70 all the way up into the positive region, positive 50 or something like that. Okay? So we're going to see a rising phase of the action potential. It's going to then drop down pretty soon after that. Those sodium channels are going to close. Sodium will stop rushing in. We're going to balance things out by sending potassium out of the cell. And then we're going to get back down to normal. We actually go through a third phase called hyperpolarization, where the neuron is actually lower than negative 70. Or even more polarized than normal. And this is because we've pumped so much potassium out of the cell that we're now even more negative, and we need to pump things back with our sodium potassium pump just to get back to resting potential. Looking through that in a figure can help. Right? So here we're sitting at rest around negative 70 millivolts. Here we get some IPSPs, some EPSPs. We get a little stimulation, some excitatory signals, and we hit threshold. And we're going to get this rising phase in red where the sodium channels open up. Potassium channels try to compete, but the sodium channels open up, and all this sodium rushes in because of all that diffusion pressure. And we go from negative 55 or so all the way up into the positive range. We get this electrical burst. Okay? We hit peak, and the sodium channels are going to close again at a new signal here in the positive range. The sodium channels close on up. We stop the rush of sodium in, and we repolarize. We get back down to normal because those sodium channels are pumping that sodium out of the cell, trying to balance things back down. Okay? In fact, we hyperpolarize a little bit. We overcompensate a little bit here, and then we need to get back to normal with our sodium potassium pump. And that's the action potential. We've set up the resting potential so this can happen basically automatically as long as we open those channels and then adjust to get back to normal. And that's how your brain works. That's how we're going to send signals from one neuron to another neuron. How we send signals from your finger to your brain when you get burnt on the finger, right? We're going to send this signal, boom. We're ready to go with the resting potential. We send a burst of electrical signal just like this.
In this lesson, we will take a much closer look at the mechanisms by which an action potential is generated at the axon initial segment. Let's focus in on the axon initial segment and action potentials originate. Recall that the membrane potential of a neuron at rest is relatively constant despite the high pressure acting to drive sodium ions into the cell. This is because the resting membrane is relatively impermeable to sodium. But things suddenly change when the membrane potential of the axon is depolarized to the threshold of excitation by an EPSP. There are three key events. First, at that point in time, when the threshold of excitation is surpassed, the sodium channels open and sodium ions rush into the cell through the membrane at the axon initial segment. This is the beginning of the rising phase of the action potential. Second, as the membrane potential is depolarizing due to the influx of sodium ions, the voltage-gated potassium channels open, and potassium begins to leak out of the cell. Third, once the membrane potential depolarizes sufficiently, the sodium channels become inactivated, stopping the sodium from leaving the cell. This is the end of the rising phase of the action potential. But the potassium channels are still open, so potassium continues to leave through the membrane. This is the beginning of the repolarization phase of the action potential. Potassium continues to leave through the membrane until such a time that the cell is repolarized and the potassium channels begin to close. The closing of the potassium channels marks the end of the repolarization phase of the action potential. But the potassium channels close rather slowly, so the membrane potential becomes hyperpolarized, and that hyperpolarization is maintained for a period of time until the membrane returns to the resting membrane potential.
One thing to talk about in terms of action potentials is that we're going to be sending these electrical signals, but we can't send them all the time. There's what's known as a refractory period, where after one action potential is sent, another action potential cannot be readily elicited. So each neuron can only fire at a certain rate. Okay, it's pretty fast, but can only fire at a certain rate. So you can't always be sending a signal. There's what's known as an absolute refractory period, where no matter how much input you send, you can't send another action potential. And this is typically basically when those channels are open. So if the sodium channels are already open, they can't open again, right? So you can't double open, you can't double send sodium. It's not really going to work, right? So that's an absolute refractory period for a brief period of time. Relative refractory period is when you really need to signal very strongly in order to get back up to threshold again. Typically this is when you're kind of trying to return to resting state. So we've hyperpolarized, we haven't quite balanced out or unbalanced with our sodium potassium pump, and so it's going to be a lot harder to get back up to threshold for a little bit. So there is a limit, there's a functional limit on how fast your neurons can fire. Final question in this video is, how do we then get that signal to the end, right? How are we going to get the information? We've gotten it from the dendrites have received the IPSPs or the EPSPs and integrated them across time and space. They've then fired an action potential. How do we get that action potential down the axon to the end of the neuron to where it needs to go? Okay. Well, basic thing that's going to happen is that the sodium is going to travel, right? The sodium is going to move from here to here. Okay. The sodium channels are tightly packed, and so once the sodium moves from here to here, there's going to be a positive charge moving this way and this way. Sodium is going to then open the gates. So we're going to open the gates here and here and here and here and here and here and here. And the sodium will just keep on sending wave after wave and wave and wave of action potentials. Okay, so essentially we're redoing the action potential of opening the gate as we go, or the depolarization of opening the gate as we go. Okay, so that's how it's going to work normally. And then the cool thing is that those myelin sheaths that we talked about make it go faster. There's a term for this called saltatory conduction. But the general idea is that the myelin sheath that are created by glia, like Schwann cells, allow it so that we only have to do the depolarization every once in a while. Okay, so the sodium can travel down along the axon as long as there's a myelin sheath, and then it's going to depolarize here, right? And then depolarize here. Open those gates here and here. It doesn't have to open the gates at every single gate. Okay, so I don't have to unlock every gate with sodium. I can do it only occasionally. Okay? It's faster. It uses less energy. I need to do less pumping to get back to normal because there's fewer locations where the depolarization happened. Okay? So larger axons, myelinated axons, are a lot faster. They send the signal faster down the axon if you got this myelin sheath. It's a little bit like in football. It's faster to throw from here to here than it is to run the whole way down. Right? So it's faster to jump than it is to run. just a few caveats to make sure that I'm not misleading you on anything here. The model we've been talking about here with the resting state, the action potential, and the 3 phases of it, and all that sort of thing, is called the Hodgkin-Huxley model of the action potential. This works most of the time. It accounts for a lot of our neural communication, but it is a little bit too simplistic. There are a few other caveats and exceptions. There are some neurons that fire action potentials spontaneously. They don't need any stimulation at all, so no EPSPs, no IPSPs, they just go. So that's an exception. Some neurons don't fire action potentials at all, so they get EPSPs, IPSPs, signals kind of traveled in a not all or none kind of signal, and we get a little bit of excitement and inhibition and a little bit of connection between neurons, but we don't ever get that burst, that action potential at all. Most action potentials work very similar with that negative 55 threshold, the negative 70 resting potential, and then the ranging up into the 40s and 50s of depolarization. But there is variance. Variance in where the threshold is, the amplitude of it, how long it lasts, and how frequently you can do it, what the length of the refractory period is. So it used to be that we said they were all exactly the same, every action potential is exactly the same, but that turns out not to be true. And then finally, it turns out that some dendrites can fire action potentials themselves. So rather than waiting to get to the axon to fire that action potential, in some neurons the dendrites can start that action potential, and we don't have to wait to integrate down at the axon. So keep some of these things in mind. Just and more broadly, keep in mind that everything in this class is going to have some complications and some caveats. Your brain's really complex.